If you break your arm, an X-ray gives you this really clean, comforting kind of binary answer, you know?
Right.
You look at the film, you see that jagged white line across the radius, and the orthopedic doctor just points and says, well, there's the problem.
Yeah, it's very straightforward. Broken or not broken.
Exactly. It feels like engineering. We really like anatomy to be visible, structural, and perfectly categorized. But, and this is a big but, if you try to apply that same rigid snapshot logic to the human face and neck, the X-ray essentially lies to you.
Yeah, absolutely
It
does.
shows you a finished, polished cathedral. What it does not show you at all is the chaotic, high-stakes construction site that actually built it. A site where tissues migrated like ancient nomads, dragging vital nerves behind them like, I don't know, endless extension cords.
That's a great way to put it.
And where a delay of just, say, 24 hours in the womb can permanently alter the architecture of a human life.
That is the perfect way to frame this. We are so accustomed to studying adult anatomy, which is, the finished cathedral where every gargoyle just sits perfectly on its ledge.
Right.
But today, we are stepping right onto the active construction site. The embryology of the head and neck is arguably, well, I'd say it definitely is the most complex landscape in human development.
Which is saying something.
It really is. These structures, they do not simply inflate like a balloon. They are negotiated, assembled, and pieced together from distinct building blocks that originate in completely different geographical areas of the developing embryo.
So welcome to a very special anatomical deep dive. Today we're looking at the embryology of the head and neck, and we are drawing heavily on the structural spine of Chapter 5 from the textbook of Head and Neck Anatomy by Hyatt and Gartner.
Yes, a fantastic resource.
It is, and our mission today is to look beyond the static lists of muscles and nerves. We really want to understand the why and the how, because, if you've ever wondered why a single cranial nerve weaves through the jaw in such a bizarre, circuitous route, or why a surgeon knows exactly where to find a missing gland deep in the chest when it really should be up in the neck.
Right, the ectopic tissues.
Yeah, exactly. All of that traces back to a ridiculously narrow window of time in early development.
It is a profound shift in perspective. If you are a learner, perhaps an early year medical student, a surgical trainee, or even a clinician revising your applied anatomy, you might initially view embryology as this sort of academic hurdle.
Oh, absolutely. Just a dusty history of the body you have to memorize.
Precisely. And memorizing the intricacies of adult nerve-muscle relationships by rote is a torturous and, frankly, fleeting exercise.
You forget it the second the exam is over.
Exactly. However, if you understand the origin, if you know the functional logic of where a muscle started its journey and when it dragged its nerve along with it, the adult anatomy suddenly isn't just a list to memorize.
It makes sense.
Right, it becomes a visible history that you can logically deduce.
So we're not just going to read you the textbook today. We are going to trace the flight paths. But before we look at the actual bricks and mortar of this construction site, the cells and the tissues themselves, we have to look at the site manager's blueprints.
Yes, the genetics.
And what immediately stands out when you read this stuff is that the vocabulary we use to describe our own human development was actually written for a completely different species.
Right.
The literature constantly refers to the branchial apparatus.
Branchial literally translates to gill.
Which is wild.
It is, and this can be quite jarring for a first-year anatomy student. Humans, quite obviously, do not develop functioning gills. But vertebrate development is deeply, deeply conserved.
Meaning we show the old blueprints.
Exactly. If you were to look at a human embryo at roughly 4 weeks of gestation, alongside the embryo of a fish or an avian species, you would need a highly trained eye to tell them apart. We share that evolutionary inheritance.
So we are essentially looking at repurposed architecture. 400 million years ago, our aquatic ancestors needed a system of muscular arches to pump water over their gills to extract oxygen. Fast forward to us, and, well, we don't need to pump water.
Thankfully.
Right? But evolution rarely invents completely new structures from scratch. It tinkers with what is already there. So we take those ancient gill-pumping arches and we repurpose them to pump air, to chew food, to smile, to speak.
That is the underlying reality of our anatomy. In modern human embryology, we technically prefer the term pharyngeal over branchial, referring to the pharynx or the throat, simply because they never function as gill for us.
That makes sense.
But the genetic blueprints orchestrating this ancient machinery remain incredibly similar. And those blueprints are written in a highly conserved sequence of DNA known as homeobox, or HOX, genes.
Hawk's genes. Okay, these are the master architects. But how do they actually do the building? I mean, it's not like a gene has little hands to move tissues around.
No, they don't. They operate much more like a geographic coordinate system.
Oh, okay.
Hox's genes code for transcription factors. Let's break that down mechanically. A transcription factor is a specialized protein. It travels into the nucleus of a cell, physically binds to the promoter region of the DNA, and effectively turns other specific genes on or off.
That's flipping switches.
Exactly. Hox's genes don't build the jaw themselves. They tell a cell where it is in three-dimensional space. They inform a cell you are currently located at the cranial end, the front of the embryo, so you need to activate the jaw-building genetic cascade, or, you're located further down the longitudinal axis, so you need to become part of the larynx.
It's positional awareness. But those cells don't build in isolation, do they? They have to talk to each other to coordinate this massive assembly. And the text heavily emphasizes this communication network, specifically the interaction between signaling cells and target cells.
Yes. The communication is entirely chemically mediated, and it operates with ruthless precision. A signaling cell will produce a ligand. This is usually a growth factor or some sort of signaling molecule.
Okay.
The cell secretes this molecule out into the extracellular fluid. It floats over to a target cell, which is essentially waiting with this specific receptor molecule on its surface.
Like a lock and key.
Precisely like a lock and key mechanism. When the signaling molecule fits into the receptor, it binds, and that binding triggers a massive intracellular cascade.
So the key turns in the lock, and the target cell receives its orders. What kind of orders are we actually talking about here?
Well, it could be in order to proliferate, meaning divide and multiply rapidly. It could be in order to undergo apoptosis.
Apoptosis being programmed cell death, which, always sounds bad, but it's actually crucial for sculpting, right?
Immensely crucial. Think of your hands. They start as solid paddles of tissue. Apoptosis is the signal that tells the cells between your fingers to die off, carving out individual digits.
Right. Because without apoptosis, we would all have wedge hands.
Exactly. But most importantly, for our deep dive into the head and neck, the signal might cause the target cell to differentiate. It tells an unspecialized cell to permanently commit to becoming a cartilage cell, or a muscle cell, or a nerve cell.
And this specific event where one group of cells forces another group of cells to change their destiny, that's called induction.
Induction is the absolute cornerstone of embryology. And understanding induction brings us to the most terrifyingly strict rule of human development, which is the window of opportunity.
The ticking clock.
The ticking clock. Development is strictly temporal. It is a one-way street. Because these genetic cascades are turned on and off by fleeting chemical signals, the target cell must be ready, waiting, and expressing the correct receptors. At the exact microsecond, the signaling cell releases its ligand.
I always picture this like a massive, complex symphony orchestra, but with a horrifying twist. There's no conductor at the front of the stage making sure everyone is ready.
Right, there's just the music.
There's only the sheet music and a rigid, unyielding tempo. If the violins, which are our target cells, don't hear the specific cue from the oboe, our signaling molecule, they simply sit there in silence. They don't play.
That's right.
And because they missed their entrance, the rest of the song is permanently altered. You cannot rewind the tape.
That analogy captures the stakes perfectly. If that chemical signal arrives a day late, the receptors on the target cell might already be gone, or the cell might have defaulted into a different tissue type. The developmental event simply never happens. And this explains a fundamental clinical reality about congenital anomalies.
Right, because if I'm thinking about severe birth defects, like a missing jaw structure or a severe facial cleft, are those mostly happening during this induction phase rather than later on in pregnancy?
Almost entirely, yes. The most profound structural anomalies occur during this critical window of induction, roughly between weeks 3 and 8 of gestation.
Wow, that early.
Very early. If a teratogen, which is an environmental agent that disrupts development, like certain viruses, radiation, or specific pharmaceuticals, interferes during the exact moment of induction, the structure simply fails to form.
The blueprint is ruined.
Exactly. However, if that same teratogen is introduced at, say, week 20, when the organ is already fully formed and just growing in size, the structural impact might be minimal. It is all about timing.
Okay, so we have the Hox gene coordinates, we have the chemical lock and key communication, and we have the ticking clock. Now, who are the actual builders on this construction site? Because the head and neck aren't built from the standard materials used in the rest of the body, are they? The text talks about mesenchyme, which is the embryonic connective tissue that builds bones and muscles, but it notes the head and neck mesenchyme has a very exotic origin.
It does indeed. In your arms, your legs, your torso, the mesenchyme largely derives from the mesoderm, the middle layer of the early embryo. But the head and neck are special. A vast amount of the mesenchyme here derives from neural crest cells.
Neural crest cell.
These are some of the most fascinating cells in biology. They originate at the crest of the folding neural tube, up near the developing midbrain and regions of the hindbrain known as rhombomeres.
Hold on. Rhomburies? Let's unpack that word. The hindbrain is actually segmenting itself.
Yes. The early developing brain isn't just a smooth tube. It pinches into distinct segments called rhombomeres. Think of them as individual staging areas. The neural crest cells in these staging areas undergo a radical transformation called an epithelial to mesenchymal transition.
Meaning they change from a lining cell to a mobile connective tissue cell.
Exactly. They break their cellular bonds, they pack their bags, which means they lock in their specific Hox gene coordinates, and they literally crawl away from the brain, migrating down into the developing face and neck to become the bones and connective tissues.
So the scaffolding of my jaw and my face essentially crawled out of my early brain. That is wild.
It really is.
And they don't just wander endlessly, do they? They follow chemical breadcrumbs.
They navigate a highly complex extracellular matrix guided by those signaling molecules we discussed earlier. Fibroblast growth factor, or SGF, and sonic hedgehog, or SHH, are heavily involved in paving these migration routes.
Sonic hedgehog. I have to say, even years later, the fact that a genetic pathway absolutely critical to human facial development is named after a Sega Genesis character still makes me laugh.
It's a memorable quirk of genetic nomenclature, definitely. But its function is deadly serious. Another crucial molecule doing the heavy lifting here is endothelin-1. And this highlights a really beautiful collaboration.
How so?
Well, for a long time, we thought neural crest cells were the sole masterminds, dictating the entire skeletal pattern on their own. But we now know they require constant conversation with the surrounding tissue.
Right.
Endothelin-1 is secreted by the endoderm, which is the inner epithelial lining of the primitive gut tube. It facilitates the interaction between the migrating brain cells and the throat lining.
So the inner lining of your developing throat is essentially whispering structural instructions to these migrating brain cells on how to build a jawbone.
Yes. And if you knock out endothelin-1, the lower jaw simply fails to develop. The conversation stops, and the structures don't form.
Incredible. Okay, so we've set the stage. We know the molecular language. Now let's fast forward the clock to week 4 of gestation. This is the critical window. What does the site actually look like?
At 4 weeks, the embryo is tiny. It's a few millimeters long and curled into a C shape. At the very top, the cephalic end, there is a shallow depression on the outside called the stomodium.
Stomodium. Okay.
This is the primitive mouth, but at this early stage, it's a dead end. It is completely separated from the primitive throat, the pharyngeal gut tooth, by a thin, 2-layered wall called the buccopharyngeal membrane.
So you essentially have a roadblock. The mouth is completely sealed off from the throat.
It is a temporary dam, and during the 4th week, that buccopharyngeal membrane undergoes apoptosis and ruptures.
The floodgates open.
Exactly. This establishes a continuous channel from the outside world into the gut. And almost immediately after that rupture, the walls of that primitive throat begin to grow and push outward, aggressively expanding into the surrounding mesenchyme.
And this outward pushing creates the foundational architecture we've been building towards, right? The pharyngeal apparatus. When I look at diagrams of this, it looks remarkably like the segmented ridges on the underside of a vacuum cleaner hose or like the rib neck of a spacesuit.
That visual is spot on. The pharyngeal apparatus is a series of segmented bilateral swellings that form on the outside of the embryo's neck region. And this system is composed of 3 repeating interlocking parts.
Okay, lay them out for us.
First, you have the pharyngeal arches themselves. These are the solid bars of tissue, the thick ridges of that vacuum hose. They have a core of mesenchyme, which, as we just discussed, is heavily populated by those migrating neural crest cells from the brain.
Okay, so the arches are the solid, meaty ridges. Got it.
Exactly. Now, on the inside of the throat, pushing outward between those solid arches, you have the pharyngeal pouches. These are lined with endoderm.
Right.
And finally, on the outside of the embryo's neck, pushing inward to meet the pouches, you have the pharyngeal grooves, sometimes called clefts. These are lined with ectoderm, the outer skin layer.
So structurally, you trace it down the neck, you hit an arch, followed by a pouch on the inside and a groove on the outside pinching together, then the next arch, pouch, groove, and so on.
Yes, exactly like that.
And here's the absolute golden rule for anyone studying this, and I really want to emphasize this. Every single one of these arches is a self-contained, pre-packaged starter kit.
That concept is the key to unlocking head and neck anatomy. In humans, we have 5 functional arches. They develop sequentially from top to bottom. We number them arches of 6, 3, 3, 4, and 6.
Let me stop you right there because the math doesn't work. We skipped number 5.
We did skip 5. Arch V is an evolutionary ghost.
But the ghost.
Yes. In lower vertebrates, it forms robust structures, but in human development, it either never forms at all or it appears as a tiny, fleeting cluster of cells and immediately regresses without leaving any permanent structures behind. So functionally, we deal with arches the first 2, 3, 3, 4, and 6.
Good to know. Don't go looking for arch view on an exam. So what exactly is inside this starter kit for each arch?
Each arch contains 4 specific unvarying components. 1, or a cartilaginous core, which will serve as a scaffold for bone or cartilage development. 2, a muscular component. 3, an artery, specifically an aortic arch vessel.
Okay, cartilage, muscle, artery. What's the fourth?
4, and this is the most vital piece for clinical anatomy, a specific, dedicated cranial nerve.
And this is where the magic of the blueprint really reveals itself, because the chaotic, twisting adult anatomy is really just a distorted, stretched-out memory of this early, neat embryological segmentation.
Absolutely.
The rule is unbreakable. Whatever muscle develops in archfest is forever, irrevocably married to the nerve of archfest. As the embryo grows over the next 9 months, those muscle cells might migrate far away from the jaw, they might stretch across the face, they might slide down the neck, but they cannot sever their connection to their original arch's nerve.
Where the mesenchyme goes, the nerve must follow.
Yes, dragging its wiring behind it.
And that single principle replaces hundreds of flashcards. If you understand the embryological origin of a muscle, you do not need to memorize its nerve supply. You can simply deduce it.
I love that. Let's put that deduction to the test then. Let's map the construction site, starting right beneath the primitive mouth. Arch of first, the mandibular arch. What is it building?
Arch art is massive. Very early on, it splits into 2 prominences. The dorsal, or upper portion, becomes the maxillary process, which will form your upper jaw and cheeks.
Right.
The ventral, or lower portion, becomes the mandibular process, which forms your lower jaw.
Okay, so it builds the jaws. What is the cartilage core sitting inside this first arch?
The cartilage of arch first is famous. It is called Meckel's cartilage. Now here is where the mechanics get really fascinating. You might assume that Meckel's cartilage simply turns into the jawbone.
That would be the logical assumption, yeah.
Right, because that's how our arm and leg bones form. They start as cartilage models that gradually turn into bone, a process called endochondral ossification. But the jaw doesn't do that. Meckel's cartilage mostly acts as a physical placeholder, a guide wire. The actual bone of the mandible forms around it through a different process called intramembranous ossification.
Wait, so the bone just materializes out of the surrounding tissue, basically ignoring the cartilage?
Essentially, yes. The mesenchymal cells in the membranes surrounding the cartilage condense and differentiate directly into bone cells, osteoblasts, skipping the cartilage phase entirely.
Wow.
Because it's bypassed, most of Meckel's cartilage actually disappears. Its sheath becomes the sinomandibular ligament. But the very top tips of Meckel's cartilage up near the developing ear do ossify. They break off and become 2 of the tiny bones in the middle ear, the malleus and the incus.
That is extraordinary to think about. The jaw's original scaffolding just gives up, turns into a ligament, and throws its top pieces into the ear to help us hear.
It's a great example of repurposing.
So what about the muscles of arch the first? If this is the jaw arch, I'm assuming it handles chewing.
Yes. Archi produces the muscles of mastication, the powerful temporalis, the masseter, and the medial and lateral pterygoids.
All the heavy biters.
Exactly. It also spins off a few accessory muscles, the mylohyoid and the anterior belly of the digastric muscle on the floor of the mouth, plus 2 tiny tension muscles, the tensor tympani in the ear and the tensor veli palatini in the soft palate.
Right, we have the muscles. Now, the million-dollar question. What is the cranial nerve hardwired into arch of first?
It is cranial nerve V, the trigeminal nerve. Specifically, the large mandibular division of the trigeminal nerve supplies all of these muscles.
So arch first is the bite and chew arch. Everything it builds helps you work your jaw, and every single one of those muscles is wired by the trigeminal nerve. Simple, logical. Now let's step down the neck to the next ridge, arch 2. the hyoid arch?
Arch 2 sits just below the first pharyngeal groove. Its cartilaginous core is called Reichert's cartilage.
Reichert's, okay.
Since archi gave us the first two ear bones, archdette provides the third, the stapes. Reichert's cartilage also forms the slender styloid process of the temporal bone, the stylohyoid ligament, and the upper part and lesser cornu of the hyoid bone in the upper neck.
So it finishes the middle ear and builds the upper suspension bridge of the neck. Now, what about its muscles? Because this is where evolutionary history gets really fun. We have our chewing muscles from arch third. What do we need next?
As mammals evolved, we required a completely new suite of muscles, not for eating, but for communication, for protecting our eyes, and for feeding our young.
Right, facial expression.
Exactly. The muscle mass of arch third undergoes a massive dramatic migration. It starts down in the neck region, but these mesenchymal cells literally crawl upwards and spread out superficially like a mask over the entire face, the scalp, and even down the front of the neck.
They become the muscles of facial expression?
Yes. The orbicularis oculi that lets you blink and squint, the buccinator that keeps food in your cheeks, the frontalis that raises your eyebrows, and the platysma tightening your neck.
Now let's apply our deduction rule. If these muscles originated down in the neck in arch 2, but migrated all the way up to my forehead, they must have dragged their arch 2 nerve with them. So what is the nerve of arch 2?
It is cranial nerve the seventh, the facial nerve.
This makes so much structural sense. Arch 2 is the smile, pout, and blink arch. And because these muscle cells had to crawl out of the neck and spread out across the skull, they pulled the facial nerve with them. That is exactly why the facial nerve branches out across the side of the face like an open hand. It was dragged there by migrating tissue.
It is a beautiful example of form following developmental history. And I want to pause here to mention a really fascinating genetic quirk that the text highlights regarding arch 2.
Oh, please do.
The specific HOX gene responsible for spatial patterning in arch 2 is HOXA2. Now, developmental biologists asked a question. What happens if a mutation occurs and HOXA2 is knocked out? What does arch 2 do?
I mean, I would assume it just fails to grow. You get no facial muscles.
You'd think so. But biology is stranger than that. If HOXA2 is missing, arch 2 defaults. It starts reading the blueprints for arch 4. It attempts to build a second set of jaw bones and chewing muscles.
Wait, it just blindly tries to build a second jaw down in the neck.
Exactly. It suggests that the developmental pathway for arch first, the jaw, is the ancient default program for this entire region. HOXA2 is essentially a modifying override switch. It is required to actively suppress that default jaw program and sculpt the tissue into the newer, more delicate structures of arch 2. When the override fails, the default takes over.
That is mind-blowing. It's like finding old deleted code in a software program that just suddenly reactivates itself.
Precisely.
I also want to touch on a muscle we mentioned briefly earlier, the digastric muscle under the jaw. Digastric means two bellies. Why is it split in half?
This perfectly illustrates evolutionary stitching. The anterior belly, the front half of the digastric muscle, develops from the mesenchyme of arch 2. The posterior belly, the back half, develops from arch 2. As they grow, they meet in the middle and join via a central tendon.
Let me deduce this then. If the front half is arch the first and the back half is arch 2, does this single muscle require two completely different cranial nerves to function?
You are spot on. The anterior belly is innervated by the trigeminal nerve, and the posterior belly is innervated by the facial nerves. One muscle, two ancient origins, two separate power cables.
I absolutely love that. Okay, so arches are ANAHN handle the heavy machinery of the face, but as we continue down the neck, the lower arches are tackling a different engineering nightmare, which is the intersection of the airway and the food pathway.
Right.
We have to be able to breathe, obviously, but we also have to swallow without choking.
The lower arches are entirely dedicated to the pharynx and the larynx. Let's look at arch 3. It sits just behind the hyoid arch. Its cartilage forms the rest of the hyoid bone, specifically the greater cornu and the lower body.
And the muscle for arch 3?
Arch 3 is remarkably simple. It sums only one muscle, the stylopharyngeus. Its job is to elevate the pharynx, opening it up during the act of swallowing.
And the dedicated nerve that must follow the stylopharyngeus forever.
Cranial nerve niax, the glossopharyngeal nerve.
One muscle, one nerve, bottom of the hyoid bone. Easy to remember. Now, things get a bit more crowded as we reach the bottom of the apparatus. Arches the 4th and 6th. The textbook groups these together quite frequently.
Because they function as a unified protective system. The unnamed cartilages of arches the 4th and 6th fuse together to construct the rigid protective skeleton of the larynx, which is the voice box.
Right.
This includes the large thyroid cartilage, your Adam's apple, the cricoid cartilage below it, and the small, intricate cartilages that pivot the vocal cords, like the arytenoids.
So they build the box protecting the airway. How do they divide the muscular labor down there?
Arch fourth mostly handles the throat squeezing. It gives rise to the superior, middle, and inferior pharyngeal constrictors, as well as one specific muscle on the outside of the larynx called the cricothyroid, which stretches the vocal cords to change pitch.
Okay, so arch fourth is constrictors and pitch. What about six?
Arch six, on the other hand, dives inside. It gives rise to all the other intrinsic muscles of the larynx. These are the tiny muscles that actually open and close the vocal cords so you can breathe and speak.
Arch four squeezes the throat. Arch six works the vocal cords. What are their nerves?
Both these lower arches are supplied by the great wandering nerve, cranial nerve X, the vagus nerve.
The famous vagus nerve.
Yes. However, because they are distinct arches, they use different branches. Arch fourth is innervated by the superior laryngeal branch of the vagus, which targets that cricothyroid muscle. Arch six is innervated by the recurrent laryngeal branch of the vagus, which supplies the intrinsic laryngeal muscles.
Ah, the recurrent laryngeal nerve. This is the classic anatomical detour. The vagus nerve drops all the way down into the chest, and the recurrent branch loops under the aorta near the heart, only to travel all the way back up the neck to reach the larynx. Why on earth does it do that?
It is pure developmental dragging. In early embryos and in our fish ancestors, the heart, the aortic arches, and the brain were all very close together in the neck region.
Oh, I see.
The nerve simply passed under the artery to reach the sixth arch. But as the human embryo develops, the heart descends massively into the chest cavity, dragging those blood vessels with it. The recurrent laryngeal nerve, hooked onto the vessel, is simply dragged down into the chest and has to grow longer and longer to reach back up to its target in the larynx.
It's literally an extension cord caught on a descending elevator. Now, the text makes a very specific, almost pedantic point here about the actual motor fibers running inside the vagus nerve to these muscles.
It is a vital detail for neurologists, actually. While we say these arch fourth and sixth muscles are innervated by the vagus nerve, the actual motor neurons doing the heavy lifting don't originate in the vagus nucleus in the brain.
Wait, really?
No. They're technically contributed by cranial nerve X-late, the accessory nerve.
Wow.
The accessory nerve hands these fibers over to the vagus just before they exit the skull together. So the vagus is acting more like a delivery conduit for accessory nerve motor fibers in this specific pharyngeal region.
Just to keep things complicated for the med students. All right, we've built the arches, we have the jaws, the facial muscles, the hyoid suspension system, and the laryngeal voice box. But right in the middle of all this architecture, forming on the floor of the primitive mouth, is perhaps the most structurally bizarre organ in the entire region, the tongue.
The tongue is fascinating because it defies the neat segmentation we just learned. It is the ultimate embryological composite. It doesn't belong to one arch. It is aggressively pieced together from multiple sources that sews in the midline.
I look at the tongue like a massive corporate merger. You have all these different archaic departments, arch first, arch two, arch third, that are forced to fuse into one single unified organ, but they stubbornly refuse to standardize their IT systems.
Yeah, that's very true.
They all keep their original proprietary wiring. Let's trace the merger. How does the front of the tongue form?
The anterior two-thirds of the tongue, the part you can actively stick out past your teeth, is an arch-I derivative. It begins around the fourth week as a small median swelling called the tuberculum impar.
Tuberculum impar, okay.
Quickly, two much larger lateral lingual swellings appear on either side of it. These lateral swellings, made of arch-I mesenchyme, grow rapidly, overgrowing the central bump, and fuse down the middle to form the bulk of the anterior tongue.
Okay, so the front department is arch-I tissue. What about the back department?
The posterior one-third, the base of the tongue resting in the throat, forms some structures developing behind arch the first. We see a swelling called the cupula, which receives contributions from arches the second, third, and fourth.
A bit of everything.
Yes. Behind that is the epiglottic eminence from arch 3. Ultimately, the rapidly dividing tissue from arch 3 surges forward and completely overgrows the arch 2 tissue, becoming the dominant surface of the posterior tongue.
Arch 3 takes over the back, arch-I builds the front. Where do they physically meet?
They meet at a distinct V-shaped groove on the top surface of the tongue called the terminal sulcus. The point of the V faces backward, pointing down the throat.
Okay, we have an arch-I front department and an arch third back department. Let's look at their stubborn IT systems, their nerves. If the front is entirely arch west, it should be wired by the nerve of arch-I.
It is. General sensation, meaning touch, pain, and temperature, for the anterior two-thirds is provided by the mandibular division of the trigeminal nerve, CNV.
But wait, the tongue's main job isn't just feeling if your coffee is too hot. It tastes. Does the trigeminal nerve handle taste?
No, it does not. Taste is a special sensory modality. The taste buds for the anterior two-thirds are innervated by a branch of cranial nerve 7th, the facial nerve, called the chorda tympani.
Hold on, I need to push back here. Why is the facial nerve, the nerve of arch through, wiring the front of the tongue, which we just explicitly said is made of arch stantru? Didn't you say arch third overgrew arch through in the back? Where did arch third dit come from?
You're tracking the anomaly perfectly. I did say arch 3 overgrew arch 3. The arch 3 tissue is buried deep in the structure. However, during that complex spatial overlapping, the arch 3 tissue leaves its nerve supply behind, invading the anterior archi tissue to handle the highly specialized function of taste.
Wow.
Evolutionarily, arch 3 is nearby and possessed the correct sensory capability, so the nerve fibers migrated into the new structure.
That is a definition of a messy corporate merger. So the front of my tongue feels temperature with the trigeminal nerve, but tastes the flavor with the facial nerve. What about the posterior one-third, the arch third territory behind the V-shaped groove?
Because the surface is entirely dominated by arch third, the posterior one-third receives both general sensation and spectral sensation taste from a single source. Cranial nerve nax, the glossopharyngeal nerve.
Oh, that's much cleaner.
It is. And right at the very back, near the root of the epiglottis, there is a tiny contribution from arch fourth, which brings in a small sensory supply from the vagus nerve.
This is staggering. I have 4 different cranial nerves: trigeminal, facial, glossopharyngeal, and vagus, all handling sensation for one single continuous muscle in my mouth. And speaking of muscle, what about motor control? Which of these 4 nerves actually moves the tongue so I can chew and talk?
Here is the final twist. None of them.
What? None of them?
None of the pharyngeal arch nerves provide motor control to the tongue.
You're joking. If it's made of arch tissue, why isn't it moved by arch nerves?
Because the actual muscle fibers of the tongue do not originate in the pharyngeal arches at all. The arches only provide the connective tissue scaffolding and the sensory covering. The actual contractile muscle cells migrate in from completely outside the apparatus.
Where do they come from?
They originate from somites, which are blocks of mesoderm located way back in the preoccipital region, right behind the developing ear. These muscle cells undergo a massive migration, tunneling forward into the floor of the mouth to populate the tongue.
And the rule of migration states that they must drag their original nerve with them from behind the ear.
Precisely. And that nerve is cranial nerve 12, the hypoglossal nerve. It is a purely motor nerve dedicated entirely to these migrating somite cells.
So the tongue is a structure physically built by arches the third, and 4, innervated by cranial nerves V, 7, 9X, and X for sensation, but mechanically operated by immigrant muscle cells wired by cranial nerve 12.
That sums it up perfectly.
It is an absolute masterpiece of chaotic assembly. If an engineer designed it, they'd be fired immediately. But it works.
It is the ultimate proof that attempting to memorize adult neuroanatomy without understanding embryology is an exercise in futility. The map is in the history.
And as if the tongue wasn't busy enough acting as a fusion site, it also acts as a departure gate. Right at the apex of that V-shaped terminal sulcus, the textbook points out a small depression.
The foramen cecum literally translates to the blind hole.
The foramen cecum. This tiny pit is the starting line for one of the greatest anatomical migrations in the human body. Let's transition into our clinical correlations and look at what happens when migrating tissues get lost. What is leaving the station at the foramen cecum?
The thyroid gland. The primordium of the thyroid, the cluster of endodermal cells that will eventually secrete metabolic hormones, starts its life right there, on the floor of the pharynx at the back of the tongue.
But it doesn't stay there.
No, it cannot stay there. It has to detach and literally burrow downwards, migrating through the tissues of the neck to reach its final anatomical position, resting against the front of the trachea, just below the thyroid cartilage.
It burrows down the neck, and it leaves a trail behind it, doesn't it?
It does. As the thyroid descends, it remains tethered to its origin point on the tongue by a narrow, hollow tube called the thyroglossal duct. Now, normally, once the thyroid reaches its destination in the lower neck, this temporary duct undergoes apoptosis. It breaks down and disappears entirely.
But if we're entering the realm of clinical correlations, we know the word normally doesn't always apply. What happens if that duct fails to break down?
If the duct persists, it leaves a hollow epithelial-lined tract running down the midline of the front of the neck. Secretions from the lining can build up inside it, forming thyroglossal duct cysts.
And how do those present?
These typically present clinically as painless spherical swellings precisely in the midline of the neck, often in children or young adults.
Mm.
If they become infected, they can swell rapidly and even rupture through the skin, creating a draining sinus tract or fistula right on the neck.
So a surgeon assessing a lump on a child's neck has to immediately think of this embryological pathway. What if the thyroid gland itself just refuses to migrate? What if it packs its bags but never actually leaves the foramen cecum?
That results in a condition called a lingual thyroid. The entire functioning thyroid gland develops right there at the base of the tongue. As it grows, it can obstruct the airway or cause severe difficulty swallowing.
Oh, that sounds awful.
It's problematic. Alternatively, the gland might migrate, but leave active bits of thyroid tissue behind anywhere along that descent route, resulting in ectopic or misplaced thyroid tissue in the neck.
So the thyroid is burrowing down the midline. But it isn't the only gland on the move. Let's look back at those pharyngeal pouches, the endodermal outpocketings on the inside of the throat. They are busy manufacturing tissues that also need to migrate. We have 5 pouches. What happens to the first one?
The first pharyngeal pouch elongates outwards to form a structure called the tubotympanic recess. The wide end of this recess expands to form the middle ear cavity and the mastoid antrum.
Okay.
The narrow stalk connecting it back to the pharynx remains open and becomes the auditory tube, also known as the eustachian tube.
Which perfectly explains why your middle ear is directly connected to the back of your throat and why swallowing helps pop your ears on an airplane.
Precisely.
What about the second pouch?
The second pouch essentially stays exactly where it is. It forms the tonsillar fossa. Eventually, lymphatic tissue from the mesoderm invades this pocket and proliferates to become the palatine tonsils. Those are the prominent tonsils you see at the back of your throat when you say, oh.
Simple enough. Now, the third and fourth pouches, this is where the migration paths cross in a bizarre, really counterintuitive way.
Yes, this is a vital concept. Both the third and fourth pouches divide into dorsal, or back, wings, and ventral, or front wings. Let's look at the third pouch first. Its dorsal wing differentiates into parathyroid tissue. Its ventral wing differentiates into the primordium of the thymus gland.
The thymus, the crucial organ where our T cells mature for our immune system. And where does the thymus actually need to be?
The thymus has to migrate a massive distance. It descends all the way down the neck and drops into the superior mediastinum, the upper chest cavity, sitting just behind the sternum. And as it migrates caudally, it drags that parathyroid tissue from the dorsal wing along for the ride.
It takes the parathyroid tissue with it as it drops. And where does it drop it off?
It drops the parathyroid tissue off on the lower pole of the descending thyroid gland. Because it ends up on the lower half of the thyroid, we call the inferior parathyroid gland.
Okay, so the third pouch creates the thymus and the inferior parathyroids. Everyone, keep that in mind. What does the fourth pouch do?
The dorsal wing of the fourth pouch also forms parathyroid tissue. But the fourth pouch doesn't build a thymus to hitch a ride on. Its parathyroid tissue just migrates a very short distance sideways to rest on the upper pole of the thyroid gland. Thus, it becomes the superior parathyroid gland.
I want listeners to really stop and visualize the spatial geometry here. The third pouch is physically higher up in the embryo's throat than the fourth pouch. But because the third pouch hitches a ride on the thymus, which drops like an anchor all the way into the chest, its parathyroid derivative gets pulled down past the fourth pouch's derivative.
Yes. The structures completely cross paths during descent. The third pouch forms the inferior gland, and the fourth pouch forms the superior gland. This is a classic, almost guaranteed board examination question. But more importantly, it is critical surgical anatomy.
Let's paint that picture. Imagine an endocrine surgeon operating on a patient with hyperparathyroidism caused by a benign tumor, an adenoma, on a parathyroid gland.
Right.
The surgeon opens the neck, easily finds the superior parathyroid where it belongs, but the inferior parathyroid is missing from the lower pole of the thyroid. The surgeon doesn't just dig around randomly. How does the embryology dictate the search pattern?
The embryological map provides the exact flight path. If the inferior parathyroid is missing, the surgeon knows instantly that it originated from the third pouch and that it traveled with the thymus. Therefore, the missing ectopic tumor must be located somewhere along that specific descent route.
So they follow the thymus.
Exactly. The surgeon will follow the path of the thymus downwards, often finding the adenoma resting against the superior pole of the thymus deep in the lower neck, or sometimes even requiring them to look down into the mediastinum of the chest. Understanding the third pouch's journey is the difference between a successful curative surgery and a failed one.
It's exactly like tracking a lost package based on the courier-specific delivery route. Just to complete the pouch list, what about the fifth pouch?
The fifth pouch is small but mighty. It gives rise to the ultimobranchial body. These cells migrate directly into the thyroid gland and become the parafollicular cells, or C cells. These are the cells that secrete the hormone calcitonin, which is involved in regulating calcium levels in the blood.
So the thyroid gland is yet another corporate merger. The main follicles producing thyroxine come down from the tongue at the foramen cecum, but the calcitonin-producing cells migrate in sideways from the fifth pouch. The complexity is astounding. Now we've looked at the inside pouches. Let's briefly look at the outside grooves, the clefts lined with outer ectoderm. What happens to them?
The first groove, sitting right between the mandibular and hyoid arches, deepens inward. It forms the external auditory meatus, the ear canal. The tissue right at the deepest point of that groove meets the tissue pushing out from the first pouch, with a thin layer of mesenchyme caught between them. Those three layers fuse to become the tympanic membrane, the eardrum.
So the first groove becomes the ear canal. What about grooves 2, 3, and 4 lower down the neck?
They get completely buried. During the fifth week, the mesenchyme of the second arch, the hyoid arch, experiences a massive, rapid growth spurt. It grows downwards, like a curtain, completely overgrowing the second, third, and fourth grooves, and fuses with the tissue of the lower neck. This sweeping action smooths out the surface of the embryo, creating the flat contour of the human neck.
It essentially paves over the ridges.
It does. But occasionally that overgrowth is incomplete, or the space trapped beneath the curtain fails to obliterate. The trapped space is called the cervical sinus. If it persists, it leaves an ectoderm-lined cavity trapped deep under the skin of the lateral neck. This can fill with fluid and develop into a lateral cervical cyst.
And how would a patient present with this?
They typically present with a painless, fluctuant swelling on the side of the neck, almost always lying just anterior to the border of the large sternocleidomastoid muscle. Unlike the thyroglossal cyst, which is strictly midline, the cervical cyst is lateral.
Okay, good distinction.
They might go unnoticed in early childhood, but can swell during an upper respiratory infection later in life. If the cyst maintains an open connection to the outside skin or breaks through to the inside pharynx, you have a cervical fistula, which can leak mucus.
Again, the embryology perfectly predicts the location and nature of the pathology. And speaking of incomplete closures on the outside, the text mentions preauricular pits in relation to the ear. What are those?
The external ear, the auricle or pinna, is a highly complex structure to assemble. It forms from 6 discrete mesenchymal swellings called auricular hillocks that develop on the opposing edges of the first and second arches, right around that first groove. 3 on arch 1, 3 on arch 2.
So 6 little bumps.
Right. These hillocks have to grow and fuse seamlessly to form the intricate curves of the ear. If the sulci, the tiny valleys between these fusing nodes, don't close completely, they leave behind tiny skin-lined dimples or pits just in front of the ear. They're incredibly common, usually totally benign, and are just a tiny, visible memory of the arch fusion process.
It is incredible how much action is happening in the neck. Glands burrowing down, arches overgrowing each other, tissues fusing. But while all that is happening, an even more intricate, high-stakes puzzle is being assembled right in the middle of the face.
The development of the face and palate. This occurs rapidly between weeks 4 and 7, and it's a breathtaking piece of three-dimensional structural gymnastics.
Let's lay out the puzzle pieces. At week 4, we have the stomodium, the mouth opening. Above it, covering the developing forebrain, is a massive bulge of tissue.
That is the frontonasal prominence. As it grows forward and downward, 2 thickened areas of ectoderm develop on its lateral lower edges. These are the nasal placodes.
These placodes will ultimately become the nasal passages. What is the mechanism there?
The mesenchyme around the edges of the placodes starts to swell and grow outward rapidly, creating a depression in the middle. The depression is the nasal pit. The raised horseshoe-shaped edges around the pit are divided into the lateral nasal swellings on the outside edge and the median nasal swellings on the inside edge near the midline of the face.
So we have a central forehead block pushing down and 2 horseshoe-shaped nose starters on either side. How does it all converge?
It requires precise timing. The 2 median nasal swellings grow toward each other, meet in the midline, and fuse solidly together. This fused structure is incredibly important. It forms the intermaxillary segment.
The intermaxillary segment. What does this specific block of fused tissue ultimately become in the adult face?
It forms a continuous central tiller. Superficially, it forms the philtrum, that vertical groove in the center of your upper lip. It forms the anterior portion of the upper jaw, specifically the premaxilla, which contains the sockets for your four upper incisor teeth. And internally, it forms the primary palate, the small triangular patch of bone right behind your front teeth.
So the entire central drop of your face, from the lip down to the front teeth, is this one fused segment. Meanwhile, we have the huge maxillary processes of arch eye growing inwards from the sides.
Yes, the maxillary processes are pushing toward the midline. They need to meet and fuse with that central intermaxillary segment to complete the upper jaw and the upper lip. As they push forward, they also compress those lateral nasal swellings we mentioned, pushing them up and inward to form the alae, or the fleshy wings of the nostrils.
And as the maxillary process pushes aggressively against the lateral nasal swelling, they create a deep crease between them, running diagonally from the corner of the eye down to the mouth.
That is the nasolacrimal groove. Eventually, the ectodermal cells in the bottom of that groove pinch off from the surface, sink into the mesenchyme, and form a solid cord. Later in development, this cord canalizes, meaning it hollows out, to become the nasolacrimal duct. This is the tear duct that drains excess tears from the surface of your eye down into your nasal cavity.
It's all just folding, sealing, and tunneling. Now, the text mentions a very specific chemical that regulates this precise facial assembly, particularly by influencing how the Hox genes operate in the migrating neural crest cells, retinoic acid.
Retinoic acid is the biologically active form of vitamin A. It is one of the most powerful signaling molecules in embryology. The embryo establishes a strict concentration gradient of retinoic acid to guide facial patterning. The clinical correlation here is stark. Both an absence and an excess of retinoic acid can be highly teratogenic.
Meaning it heavily disrupts development and causes severe birth defects. This is why medications like Accutane, which are retinoids, carry such strict pregnancy warnings.
Exactly. Exposure to teratogenic doses of retinoic acid during this window can lead to conditions like Treacher-Collins syndrome, also known as mandibulofacial dysostosis. This is a severe condition characterized by underdeveloped cheekbones, the zygoma, malformed eyes, external ear defects, and severe underdevelopment of the mandible.
That's devastating.
It is. It highlights how exquisitely sensitive these migrating neural crest cells are to their chemical environment. You flood the site with too much signal, and the builders essentially halt construction.
So the chemical balance is absolutely vital. But let's look at what happens when the physical fusion of these facial puzzle pieces fails mechanically. This brings us to cleft lip and cleft palate. We often hear these terms grouped together in public discourse, but embryologically, they are completely different developmental failures happening at different times for different reasons. Let's separate them. What specifically causes a cleft lip?
A cleft lip is a failure of the superficial facial puzzle pieces to join. Specifically, it occurs when the advancing maxillary process from the side fails to fuse properly with the central intermaxillary segment.
So the side of the upper jaw fails to meet the central pillar under the nose.
Yes. It can range from a minor notch in the vermilion border of the lip to a full unilateral cleft extending right up into the floor of the nostril, exposing the unfused alveolar bone. If both maxillary processes fail to reach the center, you get a bilateral cleft lip, where that central intermaxillary segment is essentially left hanging, isolated in the middle of the face.
The text notes an interesting demographic statistic here. Cleft lip is significantly more common in males, representing about 80% of cases. Okay, so cleft lip is a failure of the front of the face to zip together. What about the roof of the mouth? Cleft palate.
Cleft palate is a failure much deeper inside the oral cavity, and it occurs slightly later in development, around weeks 7 to 9. It involves the secondary palate. Remember those maxillary processes pushing in from the sides?
Yeah.
As they grow inward, they each drop a horizontal shelf of tissue straight downward into the mouth. These are the lateral palatine shelves.
I want to really paint a mental picture of this because the mechanics are wild. Imagine looking into the embryonic mouth. You have the two sides of the upper jaw, and they've dropped these two flaps of tissue straight down, like two doors hanging open. And right between them, filling almost the entire oral cavity at this stage, is the massive, rapidly growing tongue.
That is the exact setup. The palatine shells are pointing down, resting firmly against the sides of the tongue. But in order to form the roof of the mouth, those shells need to become horizontal and fuse in the midline above the tongue. They physically cannot do that while the tongue is in the way.
It is sheer structural gymnastics. The tongue literally has to vacate the premises for the palate to close.
During the 7th week, the lower jaw undergoes a surge of growth, expanding forward and downward. This growth physically pulls the attached tongue down and forward. The tongue drops out of the upper nasal cavity area and settles into the lower oral cavity. The very instant the tongue drops, releasing the pressure, those two lateral palatine shells swing upward, flip 90 degrees into a horizontal position, and grow toward each other to zip together in the midline.
They flip up and zip shut, creating a solid floor for the nasal cavity and a solid roof for the oral cavity, so a cleft palate.
Occurs when those lateral palatine shells fail to achieve midline fusion. This leaves a direct, open communication between the oral and nasal cavities, making feeding and speech incredibly difficult. The failure can happen for several reasons. A failure of the shelves to ascend because the tongue didn't drop in time, a failure of them to grow wide enough to meet, or a failure of the epithelial seam between them to break down and allow the mesenchyme to merge.
And interestingly, while cleft lip was heavily male-dominated, isolated cleft palate is more common in females, about 67% of cases.
The embryological timing provides a fascinating potential mechanism for this disparity. In female fetuses, the entire complex process of palatal fusion is naturally delayed by about 1 week compared to males. That extra week is a longer window of vulnerability. The longer those shelves stay open and unfused, the higher the statistical chance that an environmental teratogen, a genetic hiccup, or a mechanical delay will interfere and prevent fusion entirely.
Missed windows of opportunity. It all comes back to the ticking clock. This intricate, high-stakes choreography of the face and palate perfectly illustrates the core principle we've been circling this entire episode.
Indeed, it forces us to view anatomy not as a static list in a textbook, but as the study of structure in service of function. And crucially, how the development of that structure shapes our vulnerability to disease, the necessity for surgical intervention, and the ultimate clinical outcome for the patient.
We have covered an immense amount of ground today. The main takeaways are profound, really. The head and neck assemble from the pharyngeal apparatus, a repeating ancient blueprint of arches, pouches, and grooves. The nerve and muscle relationships you are forced to memorize as an adult are rigidly dictated by their embryonic origins. Where the arch tissue goes, the nerve follows. And most congenital defects, from cysts to fistulas to severe facial clefts, are largely a matter of disrupted timing, missed windows of chemical induction, or failed tissue migrations.
It is a dynamic, perilous, and miraculous journey from a single fertilized cell to a functional human face and airway.
Which leaves me with a final, somewhat provocative thought to mull over. We've seen how human facial development is heavily reliant on these ancient genetic pathways, these Hox genes and signaling molecules inherited from gill-bearing ancestors hundreds of millions of years ago. Evolution didn't start from scratch. It built our modern airway on top of an aquatic scaffolding. If that is true, what other evolutionary remnants are quietly shaping our modern vulnerability to disease? We aren't perfectly engineered machines. We are walking histories, cobbled together from the parts of our ancestors.
A sobering and endlessly fascinating perspective for any clinician to keep in mind.
All right, let's transition into our learning reinforcement phase. For our listeners studying for boards or exams, we are going to test your newly integrated mental models. We aren't just going to read out a list of multiple choice options. Let's work through some clinical scenarios conversationally to see if we can deduce the answers using the rules we've just learned.
Excellent. Let's focus on anatomical relationships, functional reasoning, and clinical application.
Here is the first scenario. Imagine you're looking at an X-ray and you note a fracture involving the styloid process of the temporal bone. Based on developmental origins, which other structure shares the exact same embryonic cartilage source as that fractured styloid process? Your options to consider are the incus, the malleus, the thyroid cartilage, or the stapes.
Well, the listener needs to trace the styloid process back to its origin. The styloid process develops from Reichert's cartilage, which is the cartilaginous core of the second pharyngeal arch, the hyoid arch. So we're looking for another arch-to-pharynx derivative.
Let's rule them out, the incus and malleus.
Those derive from Meckel's cartilage in arch day, so they are incorrect.
The thyroid cartilage.
That forms the laryngeal skeleton lower down, originating from arches the first and some six. Incorrect.
That leaves the stapes.
Yes. The status is the third middle ear bone, and it shares its origin with the styloid process in arch thing.
Perfect deduction. Let's try a functional reasoning scenario. A patient comes into the clinic. After a thorough neurological exam, you determine they have completely lost general sensation, touch, and temperature, specifically to the anterior two-thirds of their tongue. Based on the blueprints we mapped out, which pharyngeal arch derivative is compromised?
The key here is the geography of the tongue. The anterior two-thirds is the front department of our corporate merger. It develops from the tuberculum impar and the lateral lingual swellings.
which we established are derivatives of the first pharyngeal arch.
Exactly. And because it is archie tissue, it must receive its general sensory innervation from the nerve of archdere, which is the trigeminal nerve. Therefore, the failure traces back to an archie derivative.
Now, a tricky distractor here might be the preoccipital somites. A learner might remember those migrate into the tongue.
Yes, but the learner must distinguish between sensation and movement. The somites provide the motor muscle fibers to move the tongue, but they do not provide the sensory covering. Sensation belongs strictly to the arches.
Brilliant. Okay, let's go back to our endocrine surgeon. During a neck dissection, the surgeon finds ectopic parathyroid tissue, but it's not near the thymus. Instead, it is found resting high up, right against the superior pole of the thyroid gland. Which embryological structure did this specific piece of tissue originate from? Was it the second, third, or fourth pharyngeal pouch?
This tests the crossing migration pathways we discussed earlier. The tissue is at the superior pole of the thyroid.
Right, so it's the superior parathyroid gland.
And we know that the third pouch drops way down into the chest with the thymus, dragging its tissue to become the inferior parathyroids. The fourth pouch, however, only migrates a short distance and forms the superior parathyroids. So if the tissue is high up, it came from the fourth pharyngeal pouch.
You just follow the flight path.
Yeah.
Scenario 4. A newborn is diagnosed in the delivery room with a unilateral cleft lip. A concerned parent asks the pediatrician what exactly failed to close. As the physician, how do you explain which two embryonic structures failed to fuse?
You need to recall the superficial puzzle pieces of the face. The center of the upper lip is formed by the intermaxillary segment, which drop down from the forehead region. The sides of the upper lip are formed by the maxillary processes growing in from the sides.
So a cleft lip is the failure of the maxillary process to reach and fuse with that central intermaxillary segment.
Yes, and it is crucial to distinguish this from the lateral palatine shelves. If the palatine shelves fail to fuse, you get a cleft palate, deep inside the mouth, not a cleft lip on the surface. They are distinct developmental events happening at different times.
Let's do another functional one. The muscles of facial expression, the ones letting you smile or furrow your brow, are capable of moving the skin of the face because they migrated extensively during development, crawling up from the neck. Which cranial nerve were they obligated to drag with them?
This relies on the golden rule of arches. The muscles of facial expression originate exclusively in the second pharyngeal arch. The designated hardwired nerve for arch 10 is the facial nerve, cranial nerve 7th. No matter how far those muscles migrate across the skull, they must pull the facial nerve with them.
The smile and pout arch gets the facial nerve. Let's finish with one more anatomical relationship. If a developmental anomaly prevents the second arch from properly overgrowing and obliterating the grooves below it, what is the most likely clinical presentation a doctor will see years later?
Normally, that massive downward growth spurt of the second arch paves over the second, third, and fourth grooves, leaving a smooth neck. If it fails, that ectoderm-lined space is trapped beneath the skin.
And an ectoderm-lined space trapped under the skin will secrete fluid and form
A lateral cervical cyst. It will present as a swelling on the side of the neck, usually anterior to the sternocleidomastoid muscle.
And why wouldn't it be a thyroglossal duct cyst?
Because a thyroglossal cyst is a remnant of the thyroid's descent from the tongue, which happens strictly down the midline of the neck. Groove anomalies are strictly lateral. Location is everything in diagnosis.
Location is dictated by development. And with that, we close the textbook on Chapter 5. We started by picturing an X-ray of a cathedral, orderly and complete. But I hope that now, when you look at the human face and neck, you don't just see the finished stone. I hope you see the scaffolding. I hope you see the chaotic, time-sensitive, wildly intricate construction site that had to assemble perfectly in the dark millions of times over to create the anatomy we study today. It is truly a marvel.
A masterclass in biological engineering and evolutionary adaptation.
Keep looking for the scaffolding. Here are the details of this episode.
Embryology of the head and neck, byline, where form is negotiated before it exists, timing, fusion, and migration shaping the architecture of the face and airway.